So, big data, the future is here. Maybe the future is approaching very fast, and faster than any of us can imagine, in fact. I'm a mathematician, as Alison said. Maths. Let me show you a picture of a mathematician. The author at work in his private study, aided by the isolator. No outside noises, the worker can concentrate with ease upon the subject at hand. Actually, he's probably thinking about something rather beautiful like the shape of soap bubbles. But mathematicians can't actually be like that all the time, and they've done a lot of really positive things. For example, on the positive side, you can think about the internet, computers and data, Google, Facebook, sequencing the human genome, TomToms. In fact, mathematics is infiltrating almost every area of our present life, and a lot of really positive things have come. But on the other hand, disaster movies sell well, so let me tell you some disaster stories. So I want to talk about, the theme is really maths and data, how the two things can get together, what happens when you put them together. On February the 25th, 1991, the US Army base, I'm going to start with some rocket science, at Dhahran was hit by a Scud missile. 28 people were killed and 100 injured. And yet it was protected by the Patriot missile defense system. And somehow one of Saddam's Scud missiles sailed straight through that. Let me tell you why that happened. They took, computers think in base 2, and they took the number 1/10 and they wrote it out in base 2 numbers. 0.0001, 1, 0011, 0, it's a repeating decimal, 0011. They chopped it off after 24 places. Then they let the Scud missile thing run for the tracker thing run for 30 hours. And by that time, there was a 2-second difference because of the chop-off after 24 different decimal places. And so it got the position of the incoming Scud missile wrong. It sailed straight through the defense. It was an example of where the people programming the thing didn't understand the implications of the mathematical model. Another one. So 28 people died, 100 people were injured, despite the Patriot impregnable defense system. Now I'd like to tell you about Ariane. No, not that Ariane. This Ariane. Watch what happens. Décollage, it means lift off in French. Ariane was an EU space mission. It blew up on June the 4th, 1996, because of an elementary mathematical error. What happened there was the tracking system had 24 digits, and they'd only left 16 digits in the computer program where they wanted to store it. They stored it in the wrong place. As a result, 500 million euros and over a decade of development was wasted. So we have to be fairly careful when we're doing maths and data together. Here's another more practical problem about cyclones. In 2011, Cyclone Yasi hit Queensland. I'd like to show you what happens. So here's the cyclone. It's starting off near Fiji somewhere, and it's coming towards Australia. And we're trying to figure out where it's going to cross the coastline there. And actually, 100 meters of difference at Fiji makes 200 kilometers of difference about where it crosses the coastline. You have to know these things so accurately. And can you see it's just crossing the coastline there? And a lot of damage was done at Port Douglas, which looked like this beforehand, and like that afterwards. If we could get better, more accurate data analysis, assimilation of the data into our weather models, we could have known where that was going to happen and evacuated Port Douglas before it happened. But it was just unpredictable. computers, mathematics, and data, what could go wrong? Is it a dangerous mix that we should avoid? Well, we can't avoid it because it's happening more and more the whole time. The last half century has seen an immense growth in computing power. It's almost unbelievable. Are any of you old enough to remember the old disk drive? So a computer, this machine, has no brain. Please use your own. Disk drive, does that bring back a memory? People used to drive cars around like this in the United States. We've come a long way since the disk drive. In fact, every decade we get about 1,000 times as much computing capacity. In 1965, Gordon Moore, who was the head of Intel at the time, suggested that every year we would get twice as much, we would need twice as many components into the computer, twice as many processors, which was good for the business for Intel. And he thought that might last for a decade. And that got translated into there's twice as much information available. Well, actually, that has continued to be true every decade since. So twice as much per year, 2 to the 10th is 1,024, so call it 1,000, round it a bit. That means every decade we get 1,000 times as much information as the previous decade. People thought, oh yeah, it's just going to last up till 1975, but then in 1985 it had happened again, in 1995 it had happened again, 2005 it had happened again, 2015 they're saying, it's starting to level off, but it actually doesn't show any signs of leveling off. So what's happening is, each decade, 1,000 times more info is being pumped into the world. So we're now measuring our information in something called petabytes. A petabyte is nothing to do with a pet. It's actually a very large number. It's 1,000 to the 5th, or 1,000 times 5 years. So that's 10 to the 15th. That's a 1 with 15 zeros after it. So it's thought that, to give you some idea of the scale of that, it's thought that the amount of memory in the human brain is about 2.5 petabytes. And 1 petabyte of average MP3 encoded songs would take about 2,000 years to play. So that if you actually were somehow able to record your memory onto an MP3, then you could play it back to your ancestors. It would last about 5,000 years. It could still be playing under the nth generation, and here is a dead person with their memory being played through an MP3. So that's a lot of, if you think, just think of your memory playing for 5,000 years. We've got that amount, that's a petabyte. That's a huge amount of data. The next step is the exabyte, which is 1,000 petabytes. And according to reliable estimates, we'll have about 40,000 exabytes of data by 2020. That's 5.2 gigabytes for every person on the planet. So what can we, what's this about? Well, from the strategic point of view, big businesses are looking at this and thinking, wow, money. So for big businesses, they've seen competitive pricing push their prices down. They've offshored everything to India, and everything possible, even people sending their documents to be typed in India these days, because people there are very educated and type it a lot cheaper. They have tried economies of scale, have squeezed it to the limit, and they see that data, their data set, is the one remaining thing they can make money from. So big data. Big data was a term invented by McKinsey's. They were trying to sell their data analytics services to the US companies and to the US government. So big data has now gained priority at the government level in Australia, in the UK, in the US, Europe. All governments are saying, we need to understand this big data. All businesses are saying, we want to make money from big data. How can I monetize it, my friends say? What is big data? Well, nobody can quite tell you. It has the following properties. It's got volume. That means there's a lot of it. Velocity, that means it comes in very fast. Variety, it comes in not just on your annual profit and loss statement, but from a lot of different things like Twitter and so forth. And veracity, which means you better believe it, baby. So these are the things that attract companies to be thinking about monetizing their big data. It needs very large computers to store, and it's costly to move from one site to another, which is good for the computer companies, and handling it requires the employment of people called data scientists, and we're trying to educate some of those at UTS. In fact, here's a plug for our new analytics degree, which we're offering for the first time this year and the second time next year. We'll be training people to actually go out and make some sense of these big data things. Here's a graph from the US Forbes magazine, which demonstrates why companies using big data are making more money than that. So on the horizontal scale, the x-axis, we've got time in months, and this is the amount of money you might make if you invest something. With big data, they reckon that you can get the blue line amount. Now, I'd like to show you the amount of money. These are millions of dollars up the axis there. And can you look at the difference between the top of the red graph and the top of the blue graph? Now, the interesting thing is to look at the scale on the x-axis. So after 3 years, you can see an incredible gap between the red line, which is without big data, and the blue line with big data. No wonder all the companies are rushing to do big data. So that's with big data analytics and traditional data warehouse. So scientists and government agencies are also starting to use a lot of big data. Everybody's using it. CERN, this is from the CERN computer, Centre de Calcul, and they are producing, when they were looking for the Higgs boson, they produced about 200 petabytes of data from more than 800 trillion collisions looking for the Higgs boson, which they finally found. That's just a mind-boggling amount of data. We've got the square kilometre array here in Australia looking for very small and very rapid events in the night sky. They've gone off looking for very long events. They're looking for short events in all the data that they're collecting. The human genome, that's a picture of the genome somewhere. It is requiring a huge amount of data to analyse it. In the UK, where I just was, the NHS is planning to save the genetic profile of every UK resident in order to have a better diagnostic health tool. So when you go to the doctor, they don't just look at you as general overall health thing, they look at your individual genetic profile and they can prescribe the medicine that you need differently for each person. They need to save around 200 petabytes of data to make that happen. Closer to home, Woolies has reward cards, and every time you shop in Woolies, they are recording what you buy, and then they're directing ads to you, to your computer, etc., to tell you what's offering. There was a great story somebody told me about a guy who lent his rewards card to his daughter, and then he started getting little ads for baby products, and he didn't know that his daughter was pregnant until he started getting these things. Anyway, it turned out that she had bought some hand cream without perfume in it, suitable for ladies who are expecting a baby. And anyway, so we have to be a bit careful with these data things, but data is coming and everybody's using it. People are thinking about the shape of data. So while we're rushing headlong into large data sets, data science, I think, is still at a very early stage. And we really have to avoid Ariane-style disasters with our health systems. You know, we don't want to use the wrong algorithm and prescribe the wrong medicine. We'd ideally like our fathers not to discover that we're pregnant by these processes. So let me talk a little bit about data sets. They can be incomplete, inaccurate, inconsistent, or redundant. None of these are good things. But basically, when it comes in with great velocity and volume, this is the kind of thing you have to face. Mathematical and statistical techniques can help fix them. Numerical analysis and interpolation can fill in the incomplete data. Probability theory can also be used to fill in gaps between data points. Statistical methods can remove inaccuracies and inconsistent data. And even geometry and topology can find and remove redundancies in data. In fact, many of the best ideas from maths over the past 50 years are now being used for data. We've all heard of the butterfly effect, where a small butterfly waving its wings can cause a cyclone. Well, we just saw that with the tropical cyclone. A very, very small, it wasn't quite a butterfly, but a very small variation over a rather short period can cause a huge difference. And fractals and chaos seem natural in many phenomena. So here's an example of a fractal set. It's actually a cabbage. The idea of a fractal is if you look at it at large scale and then look at it at smaller scale, you see nearly the same thing, and then look at it at tiny scale, you keep seeing the same kind of structure. And you can kind of see with that, if you take the big picture and then you focus down on a smaller area, it kind of looks the same as the big picture. This is a very different way of thinking about data than thinking about a grid of points and interpolating between them. So we need to think about this. The brain actually processes data in a different way, and it can see many scales simultaneously, and we need to actually develop this kind of idea about when we're dealing with our data. So a data or a computer model can be understood as a discrete version of a continuous kind of reality, and that's a way of trying to understand how that discrete version goes to something continuous. I'd like to tell you about some maths that is happening very recently, which gives us a whole new way of thinking about data. It's called the maths of barcodes. No, not that kind of barcodes, those are the commercial ones. Robert Grist is a mathematician from Penn State. Here he is thinking about the blue-eyed islander problem. That's a completely different problem which I'd love to tell you about sometime. That's the riddle of the islander who committed mass suicide when they find out that their eye colour is the same. Anyway, that's a great problem. Google it sometime. Anyway, he wasn't thinking about that when he invented the theory of barcodes. Here's a data set. I'd like to show you what you can do with your data set. That's a new way of thinking about it. That's got this kind of scale invariance and gives you a new way of thinking about data. So the data set might be the weights and the heights of the population of Sydney. Well, there's more population than that, so it'd obviously be a much larger set, but let me illustrate it to you with these smaller things. Think of them. I'm going to do something like balloons. I'm going to blow them up. So I'm drawing little circles around them. And then I'm going to make those circles bigger and bigger until they just form one amorphous mass, which was what the last slide was. So can you imagine just blowing up each of these data points, just putting little circles around them? And these might be three-dimensional data with spheres around them, but anyway. So let's see what happens. See how those ones there have joined up? There's a little shape you can start seeing there. This is a circle there. There aren't any other circles yet, but there's a circle there. So I'm going to isolate those that little circle there and put it over there like a little, well, it's some sort of shape, but it's like a closed section in my graph, yeah? And now I'll make them a bit bigger and I get that shape. If I keep going, I'm going to represent my data sets like this. See what I'm doing? Whenever they join up, I'll draw a little line between them. And so I get a little shape like that. Now that shape occurs just at the radius that I've blown them up. If I blow them up a bit more, I'll get different shapes. And the shape will change as I blow them up a little bit more, yeah? And they'll start not only making little cycles, but they'll start filling right in, and then I'll fill in like that. So this is a way of thinking about data sets, but thinking about the scale changing at each point. Let me just keep doing it. And so I get these wonderful graphs of all the data all joined up. Looks a little bit like that bubble pattern that the mathematician was looking at the first place, doesn't it? So his Grist's barcodes is I'm going to count the number of circles and the number of lines I get. So H0 is the zero, it's called homology groups. It's something you can compute about topological shapes. I'll write a line for each of those, and my little radius of the circle, which is called epsilon, every mathematician has to have an epsilon in his talk, gets bigger and bigger, and then I see how many blobs there are, how many circles there are. Here there's one three-dimensional thing with it all filled in. There are circles, so at various different stages of epsilon I get different graphs. And so that data set that I started off with is represented by these barcodes here. We've started with the data set, we've transformed it into something else we can think about. And whether there are cycles or not tells you how well the data is representing the reality. It's a really cool idea. It's using some quite advanced maths, and it's a completely new way of thinking about data. So people are doing this kind of thing. And so there you can see that at the end stage, you've only got one blob left because they've all joined up. At that stage, there's still only one. At this stage, you've got the big blob, but you've got a cycle or two, so etc. I'm trying to get the engineering faculty to represent this kind of thing in their data warehouse. I think I'm having some success, but it's taking a little while to impinge on them. But this is a great different way of thinking about data, which uses some really sophisticated and fun maths, but which actually is going to tell you how to handle your data. So my real point of doing this, or partly I have the joy of displaying to a general audience some really nice maths, but partly there are clever people thinking about how to analyze data better and how to use it better. So the human brain can use data in many more ways than the traditional approach of applied maths and computing. And computing scientists are really studying how the human brain processes data. Artificial intelligence people are trying to mimic the brain's approach to treating large amounts of data from varied inputs. And actually thinking about are there cycles in the data is kind of what your brain does, actually. So some of these methods and approaches that I've been talking about are key mathematical techniques to align with AI. I think that the next 20 years are going to see a complete revolution in what we can do with data. And it's going to need increasingly sophisticated mathematical techniques to help us do it. Unfortunately, at the same time, there's a kind of math phobia happening in the West. Certainly at the level of math studied at school. We're seeing fewer and fewer people taking 4-unit maths. They're all going down to lower and lower levels of maths. So there's this schism growing up in society where people are afraid of it, and yet it's being used more and more and more to generate our health, our shopping, our internet. Everything is reliant on some perhaps reasonably sophisticated mathematical model. There's been a lot of public debate about the sinister use of data. And a lot of this is really, in fact, about the mathematical algorithms which are everywhere and which are lying behind what people are concluding about the data. I and my maths friends don't share this sinister view, but then we have a feeling for how the algorithms work. You know, we understand really what's going on, or at least we believe we do, and mostly we do. But I'm sure we can find out. We need to understand the algorithms and what their limitations are and how they're likely to develop and what they're likely to show. My conclusion is that actually we need a more mathematical society. We need more people to understand more of these things so that there's less mystery about them. So this is a plea for you to tell your kids to do higher level maths at school. Otherwise, this 1,000 times data coming every decade is just going to overwhelm us, and there'll be very few people who understand that, and the rest of us will just be slaves to the whole industry. So that's my kind of conclusion from this talk, and it's been really fun presenting it to you. Thank you very much.